Welcome back to Math 250. I hope that everybody, you and your families are all safe and sound from the hurricane, and everybody's safe and healthy. Okay, so welcome back. Okay, so let's begin today's lecture. Today's lecture will be in two parts. Today's lecture will be in two parts. The first short part will be sort of like a motivation for exponentials. Motivation for exponentials. And this is just a short part. It's sort of philosophical. It's not test material. It's mainly for you to see the big picture. So it's philosophical. It's mainly philosophy, not test material. And not test material. Okay, it won't be in any test. Okay, this won't be in any test. Okay, let me make sure that everybody's seeing everything clearly. Okay, so this won't be in any test. This is just to make sure that you see the big picture. And the second part today, this will be most of the lecture, so this will be the long part. The long part will be where we work through some homework 2 questions. So work through some homework 2 problems. Okay, we'll work through some homework 2 questions. Okay, let me check to make sure that everything's clear. Okay, so this is today's lecture. First, a short part. This is today's lecture. First, a very short lecture to motivate exponentials. This is just something to help you see the big picture, and this is not test material. This is just to increase your understanding by looking at the big picture. And second part is where we work through selected homework 2 questions. Okay. So let's do the first part, the philosophy of exponentials, okay, motivating exponentials. So first of all, what are the 2 important types of functions in this class? What are the 2 most important classes of functions in this course? So what are the 2 important types of functions in this course? What are the 2 types of functions that are the most important types of functions in this course? The first most important type of function, the first most important type of function in this course are the polynomials. The polynomials especially the degree 1 polynomials, namely the straight lines. Especially the straight lines. Okay, so let me check to see if you can see this. Okay, so the first most important type of function in this class, the first most important type of function in this course are the polynomials, especially the straight lines. And the second the second most important type of function in this class will be the exponentials, the exponential functions. Exponential functions. So these 2 types of functions are the most important types of functions considered in this class. Okay, so these 2 types of functions, polynomials, especially straight lines, and exponential functions, these two are the most important types of functions considered in Math 250. Okay, why is this so? Why is this so? Well, it's easy to see why straight lines are very important in this course. Well, first of all, they're the nicest functions in the universe, right? They're the nicest functions in the universe. Straight lines are the nicest functions of all. Right? Straight lines are the nicest functions in the universe. And whenever you study anything at all, whenever you do a scientific study of anything at all, you always start by studying the nicest case first. You always start by studying the basic and the easiest case first. And straight lines are basically the easiest case, the most basic case. I mean, this is the case that you first study in school. So since these are the nicest functions in the universe, we always study them. We always study it first. In any scientific study, when you study anything at all, you always study the nicest case first, the easiest case first. And straight lines are the easiest case. So then we begin by studying straight lines. So it's pretty easy to see why straight lines, polynomials, especially straight lines, are the first most important type of function for us to study. But let me also add something else about straight lines, and that is even for more complicated functions, even when you have a more complicated function, you can often locally approximate them by straight lines. You can often locally, meaning in small regions, reduce to the case of straight lines. This is something I mentioned a long time ago. So can locally meaning in small regions, approximate many complicated functions. Straight lines. Okay, this is something that I mentioned previously. So, for instance, if you have a very complicated function, say a function like this is a pretty complicated function. It doesn't look like a straight line at all. But in many cases, like in this case, even though it doesn't look like a straight line at all, we can often locally, meaning in small regions, like small regions of space and time, approximate this function by a straight line. Okay, so this function doesn't look like a straight line at all, but in small regions it will look like a straight line. So for instance, in this small region, it looks like a straight line, so we can approximate by a straight line. In this small region, we can approximate by a straight line. In this small region, we can approximate by a straight line. So for many complicated functions, even though they don't look like straight lines, in many cases, locally in small regions, we can approximate by straight lines. So that's one reason why polynomials, but especially straight lines, are the first most important type of function that we study in this course. First, they're the nicest functions in the universe. So in any study that you do at all, in any subject, you always begin with the nicest case first. And secondly, even for more complicated functions, things that don't look like straight lines at all, oftentimes in small regions, say small regions of space and time, locally, you can approximate by straight lines. So this small region, and so on and so forth. Okay, so that's the first most important type of function in this course. Polynomials, especially degree 1 polynomials, straight lines. The second most important type of function in this class, in this course, that we'll study are exponentials, exponential functions. So of course, again, you ask why. Why are we interested in exponential functions? Why are exponential functions the second most important type of function to study in this course? Okay, now remember what this course is. What is this course? Okay, this course is calculus for business and the social and biological sciences. Okay, so recall that. This course is calculus for business and the social and biological sciences. That's what this course is. Let me again check to make sure that the writing is clear. Okay, Okay, the lecture already is. So that's what this course is. It's calculus for these areas, business and the social and biological sciences. And it turns out, in many of the examples that occur in these areas, in many of the examples, the model is exponential. In many of these examples, the model is captured by an exponential function. So, for example, in things like population growth, so, for example, you might be interested in modeling the population growth of a bunch of bacteria, a bacteria colony, e.g., bacteria colony. Then the model, the most basic model, is exponential. And even the more complicated models will involve an exponential in some way. Another example is compound interest. Compound interest, again, is something that involves an exponential, and many other models too. These and many other models from these areas involve exponentials. They use exponential models. They so involve exponentials. Okay, so it's like exponentials are something that just occur over and over again in these areas. It's just like, for instance, in physics. In physics, if you're interested in harmonic motion, like spring motion, right? Some sort of periodic motion, like spring motion, then you have to study sine functions and cosine functions, because those types of functions play an important role in harmonic motion, periodic motion. So similarly, in these areas, business, social and biological sciences, exponential functions pop up a lot. So that's why exponential functions are the second type of important functions in this class. Okay, so for this class, the two most important types of functions that we'll be studying are polynomials, especially straight lines, linear growth, linear functions, degree 1 polynomials. Okay, polynomials, especially straight lines. And the second most important type of function that we'll be studying are exponential functions. Okay, let me tell you a key property of exponential functions. Here's a key property of exponential functions. It's sort of like a characteristic property. This is sort of something that characterizes exponential functions. Now, I'll say more about that later on. Okay, I'll say more about that in future lectures. So here is a key property, a characterizing property of exponential functions. So key property of exponential functions. I'll just write exponentials. So a key property of exponentials is that whenever you have an exponential function, the slope, or if you prefer, the rate of change, or if you prefer, the growth rate, whenever you have an exponential function, the slope, or the rate of change, is proportional to the size. And this is a key property of exponential functions. So the slope, or growth rate, or if you prefer, rate of change, the slope or rate of change, or preferred growth rate or rate of growth of an exponential function, I just write exponential, is proportional to size. So this is a key property, a characteristic property of exponential functions. Okay? A key property of exponential functions. And I'll explain more about that. I'll describe that in greater detail in future lectures. But a key property of exponential functions is that the slope, or if you prefer the growth rate of change, is proportional to size. Okay, I'll elaborate on this. Okay, so to elaborate on this, let's contrast exponential functions with straight lines. Okay, let's contrast exponential functions with linear growth. So contrast between straight lines, or if you prefer linear growth, and exponential growth. Okay, so to understand this statement a little bit more, and we'll understand it even more, I'll elaborate even more in later lectures, but to understand it a little bit more for now, let's contrast exponential functions with straight lines. Okay, let's contrast exponential growth with straight line growth or linear growth. Okay, let's do that contrast. Okay, so first let's talk about straight lines or linear functions or linear growth. So for straight lines, or for linear growth, so for straight lines or linear growth, okay, so these are for degree 1 polynomials, right, straight lines. So functions of the form pt equals to t plus b. Okay. So for straight lines, so a characteristic property, a key property of straight lines or linear growth, a key property is that the slope is constant. Okay, that's a key property of straight lines, and that is the slope is constant. The slope or the rate of change is constant. Okay, that's the key property. So for straight lines or for linear growth, linear functions, you have the slope is constant. You have a constant slope or rate of change. That you have a constant slope or growth rate. Okay, that's a key property of straight lines. The slope is constant. The rate of change is constant. Meaning, the slope is the same at every point. The rate of change is the same at every point. Finally, at every point, the slope is the same. Slope at every point, the slope is the same. Okay, so this is a key property of linear growth. This is a key property of straight lines, and that is the slope is constant. You have constant slope. At every point, the slope is the same. Okay, the slope or the rate of growth is the same at every point. It's the same number at every point. Okay, here's an example. Example. Say that PT is a model for population growth. Say that PT is the population of a village in year T. Population of a village in year T. Okay, say that PT is the population of a village in year T. And let's say that it's a straight line. Okay, so we have linear growth. So say that PT is this straight line. 3t plus 100 people in year T. Okay, 2 years after some year which we designate as year 0, right? Okay, so say that PT is this straight line. Okay, this linear function. So then what's the slope? The slope is 3, right? The slope is 3. So the slope is the constant 3. At every point, the slope is 3. No matter what the point, the slope is 3. So in other words, the population grows at a constant rate of 3 people per year. So population grows at constant rate of 3 people per year. Okay. So at every point, the slope is the same. At every point, the slope is 3. Or more precisely, 3 people per year. At every point in time, the rate of change is 3 people per year. Okay, no matter what point you have, the rate of change is 3 people a year. So you have a constant slope, a constant rate of change of 3 people per year. Okay, let's see a picture. Here's a picture. Okay, so say that this is the straight line PT equals to 3t plus 100. Then what you have is a constant slope. At each point, the slope is 3. Or more precisely, at each point, the slope is 3 people per year. Okay? No matter what the point, the slope is the same. The slope is 3 people per year. You have the constant slope 3. So meaning, at any point in time, if you move forward by 1 year, you move forward by 1 year, the population of the village grows by 3 people. And it doesn't matter what point in time. It doesn't matter what point in time you have. At this point in time, you move forward by 1 year, the population grows by 3 people. At any point in time, because the slope is constant. The slope is the same at every point. So at this point, at any point in time, say at this point in time, you move forward by 1 year, the slope, the population increases by 3 people. Okay? At any point in time. So you have a constant slope at any point in time. At any point, the slope is the same, which is 3 people per year. So at any point in time, say at this point in time, you move forward by 1 year, the population grows by 3 people. And it's true no matter what point you are, no matter what point you have, no matter what point you're at. So this is a key property of straight lines, and the key property of straight lines is that the slope is constant. So at every point, the slope is the same. At every point, the slope is 3 people per year. Okay, so now let's look at exponential growth. And let's contrast this with exponential growth. So let's look at exponential growth. So we're looking at exponential, so something of this form. Now, in contrast to straight lines, exponential growth has non-constant slope, non-constant rate of change. So the slope at different points are different. Okay, so you have non-constant slope, or non-constant slope or rate of change. So at different points, you can have different slopes. Okay, at different points, you can have different growth rates. So in fact, as we indicated previously, for exponential growth, the slope or the rate of change is proportional to the size. Okay, so in fact, slope or growth rate or rate of change is proportional to size. So what does that mean? That means the larger the size or the bigger the size, the faster the growth rate. Or the larger the size, the bigger the slope. So, larger size implies faster growth rate, or if you prefer, bigger slope. Okay, Okay, so for exponential functions, the slope is non-constant. At different points, you can have different slopes. At different points, you can have different rate of changes or different growth rates. In fact, the slope or the growth rate is proportional to the size. The slope or the growth rate is proportional to the size, so that means that the bigger the size, the bigger the slope. The bigger the size, the faster the growth rate. And you can see that. You can see that by looking at the picture for exponential growth, right? What does the picture for exponential growth look like? This is the picture for exponential growth. And what do you see from this picture? What do you see from the picture for exponential growth? You see that this is the slope over here, this is the slope over here, this is the slope over here, this is the slope over here. And this is not really well drawn. Let's try to do it more. This should be sort of curved upwards. This is better picture. This is the slope over here, this is the slope over here, this is the slope over here, and this is the slope over here. Right? So you can see that the slopes are different. And actually, the higher up you go, the steeper the slope. The higher up you go, the steeper the slope. Right? So the larger the size, the bigger the slope. The higher up you go, the steeper it is. Right? The higher up you go, the steeper it is. This is supposed to be curved upwards, right? For exponential growth, this is curved upwards. So the higher up you go, the steeper it is. So the higher up you go, the bigger the slope. Or if you prefer, the higher up you go, the bigger the rate of change. Okay, so then that's the contrast between exponential growth and linear growth. For linear growth, the slope is the same at every point. For exponential growth, the slope can differ. And actually, the bigger the size, the bigger the slope. The higher up you go, the steeper it is. So the bigger the size, the faster the rate of change. Okay, so that ends the motivation for exponential functions. Okay, so what time is it? Okay, 27 minutes. Okay, let's now work through selected homework questions. Okay, let's now work through selected homework questions. Let's now work through selected homework 2 questions. Okay, let's now work through selected homework 2 questions. Okay, so selected homework 2 questions. Okay, so first let's do the homework 1 PDF file number 6. Homework 1 PDF. Number 6. So we're asked to simplify this expression. We're asked to simplify 2 times c d to the 4th squared c d to the 5th. Okay, we're asked to simplify this expression. Okay, let me make sure it's clear. It looks nice clear. Okay, so towards simplifying this expression, the first thing I would do is I would use the rule which says that we can distribute exponentiation over multiplication. We can distribute exponentiation over multiplication. So then I would distribute this exponentiation over this multiplication and this multiplication, and I would distribute this exponentiation over this multiplication. So first let's distribute this exponentiation over this multiplication and this multiplication. So then we get 2 squared, c squared, and d to the power of 4 times 2. And then now let's do this one. Let's distribute this exponentiation over this multiplication. So we get c fifth, d fifth. And over here, I use rules 3 and 2. Rule 3 says that we can distribute exponentiation over multiplication. And rule 2 says that repeated exponentiation is the same as multiplying the powers. Okay, so over here, we multiply the powers. Okay, now let's simplify this. This is 4 times c squared d8 times c fifth d fifth. And now Now let's bring down the 4. Let's multiply this c squared with this c fifth. We can multiply this c squared with this c fifth with the rule which says that if we multiply two exponents with the same base, it's the same as adding the powers. Okay, so over here we're multiplying two exponents with base c, so that's the same as adding the powers. 2 plus 5 is 7. And now let's do it for the d's. Let's multiply this d8 with this d5. Again, we multiply d8 with this d5 by using the rule which says that we can multiply two exponents of the same base by adding the powers. Okay, both of these have base d, so then multiplying them involves adding the powers. 8 plus 5 is 13. And then over here we used rule 1. Okay, so then that finishes this question. Okay, let's do another question. Let's do the homework 1 PDF file number 7. Homework 1. I mean, this is all homework 2, even though I'm using the homework 1 PDF file. Okay, the homework 2 is coming from the homework 1 PDF file. Homework 1 PDF file number 7. So we're asked to simplify the following expression. Negative 2 times a to the power of 3 times b squared c naught divided by 3 a squared b cubed c7 to the power of minus 2. Okay, so simplify this expression. Okay, so to simplify this expression, we're going to use an exercise that I mentioned in the lecture notes. Okay, so we're going to use this exercise which I mentioned in the lecture notes. So, exercise, this is from lecture, and the exercise says the following. It says that if we have a fraction, and if we take that fraction to a certain power, say to the power of minus r, then the exercise says that we can change the sign of the power. We can change the sign of the power, provided we flip everything inside the parentheses. And we can change the sign of the power, provided that we flip everything inside the parentheses. So flip everything inside the parentheses, so a divided by b becomes b divided by a, and then we're allowed to change the sign of the power. Okay, so then this is the exercise from the lecture notes. Okay, if we have a fraction, and we take it to a certain power, then we can change the sign of the power. We can make the minus r to an r. Okay, this is r now. We change the sign of the power, but we can do that only if we flip everything inside the parentheses. So we flipped everything inside the parentheses. A over b became b over a. Okay, so now use this exercise on this question. Using this exercise in this question, we can change the sign of this power. We can make this minus 2 to 2, as long as we flip everything inside the parentheses. So flip everything inside the parentheses. And then since we flipped everything inside the parentheses, we can change the sign of the power. The minus 2 becomes a 2. Okay, so we used this exercise up here. Exercise. Just one exercise. Okay, so using this exercise in the lecture notes, we change the minus 2 to the 2 by flipping everything inside the parentheses. Okay, next, let's simplify inside the parentheses. Let's simplify inside the parentheses. So we have a 3 on the top and a minus 2 on the bottom. So first, we divide a squared by a cubed. using the rule that says that if we divide two exponents of the same base, okay, both of these exponents have base A. If we divide two exponents of the same base, that's the same as subtracting the powers. So 2 minus 3 is minus 1. Same thing, we divide b cubed by b squared by using the rule again that if we divide two exponents of the same base, here the base is b for both of them, then that's the same as subtracting the powers. 3 minus 2 is 1. And again, we do use that rule again. If we divide two exponents of the same base, then it's the same as subtracting the powers. So C7 divided by C0, 7 minus 0 is 7. Okay, so here we use rule 5. Okay, so rule 5 says that that's the rule which says that you divide two exponents of the same base. That's the same as subtracting the powers. Next, we can make this negative 1 power into a positive power. We can make this negative 1 into a positive 1 by using the rule which says that we can move exponents up and down fractions as long as we change the sign of the power. So we move 8 minus 1 to the bottom, it becomes 8 plus 1. Right. So we move the 8 minus 1 to the bottom, it becomes 8 to the power of 1. Okay, so and the rule is we can move exponents up and down fractions as long as we change the sign of the power. So that's rule 4. And finally, we use the rules which say that we can distribute exponentiation over division and multiplication. Okay, we use the rule which says that we can distribute exponentiation over division and multiplication. So we distribute this exponentiation over this division, and we distribute exponentiation over this multiplication, and this multiplication. Okay, we use the rules which say we can distribute exponentiation over multiplication, and we can distribute exponentiation over division. So we distribute this exponentiation over this division, and this multiplication, and this multiplication, and this multiplication. So then it becomes 9b squared c14 divided by 4a squared. So this is rules 6 and 3. This should be 14, by the way, just to make it clear. These are rules 6 and 3. So those are the rules which say that we can distribute exponentiation over multiplication and division. And we also use rule 2, which says that repeated exponentiation is the same as multiplying the powers, right? Because 2 times 7 is 14. And we have this 14 over here. Okay. Next, let's do the Homework 1 PDF file number 8. The Homework 1 PDF file number 8. Here we're asked to simplify this expression. 2 times x to the power of 3/4 divided by 1/3 times y to the 4th divided by x to the power of minus 1/2. Oh, there's a cube here. Okay, so here we're asked to simplify this expression. Okay. So the first thing I would do is I would simplify this expression. And I would use the rule which says that we can distribute exponentiation over multiplication, and we can distribute exponentiation over division. Okay, we can distribute exponentiation over multiplication and division. So then I would distribute this exponentiation over this division, and I would distribute the exponentiation over this multiplication. Okay, so using the rule which says that we can distribute exponentiation over multiplication and division, we distribute this exponentiation over this division and this multiplication, and we get 8 times x to the power of 9 over 4 divided by y to the power of 1. And let's bring down the second part. Okay, the second part is the same. The second part is the same as before. Okay, so I used the rules which allowed me to distribute this exponentiation over this division and this multiplication. So I used rules 1 and 5. No, 6 and 2. 6 and 3. And also I used the rule which said that repeated exponentiation is the same as multiplying the powers. Repeated exponentiation is the same as multiplying the powers. I also use that rule because 3 times 3 over 4 is 9 over 4, and 3 times 1/3 is 1. Okay, so I also used rule 2, which said that repeated exponentiation is the same as multiplying the powers. Okay. So next, okay, let's bring the 8. And next, let's divide x to the power of 9/4 with x to the power of minus 1/2. Let's divide these two, x to the power of 9/4 divided by x to the power of minus 1/2. And let's do that using the rule which says that if you divide two exponents of the same base, it's the same as subtracting the powers. Okay? Both of these things have base x. So then when you divide x to the 9/4 by x to the power of minus 1/2, it's the same as subtracting the powers. 9/4 minus 1/2. So you get let's write this bigger. 8 x to the power of what's 9/4 minus 9/4 minus 1/2. That's 9/4 plus 1/2 is the same as 2 over 4. So that's 11 over 4. So it's x to the power of 11 over 4. Okay, so I divided these two exponents in base x, and since they have the same base, that corresponds to subtracting the powers. Similarly, let's divide 9/4 by power 1, and so again, you're dividing two exponents on the same base, and that's the same as subtracting the powers. 4 minus 1 is 3. So y cubed. So that's it. So I use rules. I use rule 5. The rule which says that if you divide two exponents of the same base, it's the same as subtracting the powers. Okay, so now let's do the next one. Let's do the homework 1 PDF file at number 9. Homework 1 PDF number 9. And in this question, we're asked to simplify this expression. 4 times the cube root of 5 squared divided by the cube root of 5 times 5 squared. And by the way, 5 is the same as 5 to the power of 1, so you just put 1 there. Okay. First, let's simplify the expression inside the bottom cube root. Let's simplify the expression inside the bottom cube root. Okay, over here. So then, let's keep the top. And then we're just simplifying the expression inside this bottom cube root. And what rule do we use? Well, we're multiplying two exponents of the same base. We're multiplying two exponents with base 5. And we use the rule which says that if we multiply two exponents of the same base, it's the same as adding the powers. 1 plus 2 is 3. So 5 to the power of 3. So we're using rule 1. We're using the rule which says that if we multiply two exponents of the same base, it's the same as adding the powers. And now, okay, over here we have a cube root. Over here we have a cube root. So now let's use the rule which says that if we have an rth root, that's the same as exponentiating by taking to the power of 1 over r. Okay, so it's rule, let me write down the rule first. Rule 8. Rule 8 says that if we have an rth root, it's the same as exponentiating by taking to the power of 1 over r. If we have an rth root, it's the same as exponentiating by taking to the power of 1 over r. So then this thing becomes, the top becomes 4 times, the cube root is taking to the power of 1 over 3, using this rule. Okay? The cube root is taking to the power of 1 over 3. So 4 times 5 to the power of 3, 5 to the power of 2 over 3, and the bottom becomes, this cube root becomes taking to the power of 1 over 3, right, by this rule. By this rule, rule 8. This cube root becomes taking to the power of 1 over 3. So that's 5 to the power of 3 over 3, right? Because there was a 3 over here. Okay, and then finally, let's divide 5 to the power of 2/3 by 5 to the power of 3/3. Using, again, the rule which says that if we're dividing two exponents with the same base, that both of these exponents have base 5. So if you divide two exponents with the same base, that's the same as subtracting the powers. So it's 4 times subtracting the powers. 2/3 minus 3/3 is minus 1/3. And so this is rule 5. Okay, the rule which says that you divide two exponents with the same base, that's the same as subtracting the powers. Okay. That's it. Okay. Okay. Next, let's do the homework 1 PDF file number 10. Let's do the homework 1 PDF file number 10. Homework 1 PDF file number 10. Okay, so this question asks us, this question gives us the equation x to the power of the square root of 2 is equal to 2. And it asks us to solve for x. It asks us to isolate the x. Okay, so let me tell you the trick. The trick is something that I explained in the lecture notes already. But I'm going to explain it again in a few minutes. Let me just solve the question first. So the trick is you take both sides to the power of 1 over the square root of 2. That's the trick. You take both sides to the power of 1 over the square root of 2. So then this becomes x squared root of 2 to the power of 1 over the square root of 2. Let me make some more space. Let me make some more space. So this left-hand side, you take it to the power of 1 over the square root of 2. And then to balance it, you have to take the right-hand side to the power of 1 over the square root of 2. Okay, so that's the trick. The trick is to take both sides to the power of 1 over the square root of 2. And as I said, this is a trick that I explained in the lecture notes, and I'll explain it again in a few minutes. And then, okay, what do we have? We have repeated exponentiation. Repeated exponentiation is the same as multiplying the powers together. The square root of 2 times 1 over the square root of 2 is just 1. So we have x to the power of 1 or x, and then we isolate the x. X is the same as 2 to the power of 1 over the square root of 2. Okay, so that's the solution. That's the solution. Let me see if it's all written clearly. Okay, it looks like it's written clearly. Okay, so this is the solution. Let me give you more explanation. Here's more explanation. Okay, so this is, as I said, this is already explained in the lecture notes, but I'll repeat it over here. More explanation. So what's the strategy? first of all, okay, so we're given this equation. Okay, this is the equation that we're given. And we want to isolate the x. We want to isolate the x. So in other words, we want to make this square root of 2 into 1. So what we want is to make x to the power of the square root of 2 into x to the power of 1. Right? Because x to the power of 1 is just x. So if we have x to the power of 1, we've isolated the x. So we want this square root of 2. We want to make the square root of 2. We want to make the square root of 2 into 1. So how do we make the square root of 2 into 1? So here's the trick. The trick that I gave you in the lecture notes. And the trick is you use rule 2. Remember what rule 2 says? It says that repeated exponentiation is the same as multiplying the powers together. So we use, okay, this over here is rule 2. Okay. Repeated exponentiation is the same as multiplying the powers together. So if we take x and we exponentiate by taking it to the power of r, and we exponentiate again by taking the whole thing to the power of s, it's the same as taking the original x to the power of r times x. That's rule 2. Repeated exponentiation is the same as multiplying the powers together. So then, what you want to do is you want to make the square root of 2 into 1, right? So what you want to do is you solve for the square root of 2 times s is equal to 1, and the answer to that is s equals to 1 over the square root of 2, right? 1 over the square root of 2 times the square root of 2 is 1. So then you exponentiate both sides by this 1 over the square root of 2. So exponentiate both sides by 1 over the square root of 2, by taking the power to 1 over the square root of 2. So that's what we did. We took this thing and we exponentiated both sides by 1 over the square root of 2. And then what does this left-hand side do? Because by rule 2, repeated exponentiation is the same as multiplying the powers together. So that's x to the power of the square root of 2 times 1 over the square root of 2. Right? By rule 2, repeated exponentiation is multiplying powers together. So this is x to the power of the square root of 2 times 1 over the square root of 2. Well, what's square root of 2 times 1 over the square root of 2? What's square root of 2 times 1 over the square root of 2? It's 1. It's 1. That's why we took 1 over the square root of 2. This is the same as x to the power of 1. So then we isolated the x. And this is the solution. Okay? So this is the explanation for this, the extra explanation for the solution. Okay? If you write this down, it'll be okay. But this is the extra explanation for the solution. Okay? The thing that I also explained in the lecture notes. Okay, let's do one more question, and then we'll end it. Let's do the homework 1 PDF file number 11. Let's do the homework 1 PDF file number 11. So we're given this equation, 3 times x minus 1 divided by 2 to the power of minus 2 over 3 is equal to 1. We're given this equation, and we're asked to isolate the x. We're asked, given this equation, we're asked to isolate the x. We're asked to solve for the x, okay, given that equation. Okay, so towards isolating the x, let's first remove this 3. Let's first remove this coefficient 3. So we divide both sides by 3. We divide both sides by 3. So we get x minus 1 over 2 to the power of minus 2/3 is equal to 1/3. Okay, so towards isolating the x, we first remove the 3 from the left-hand side. And of course, we can rewrite this 1 over 3 as 3 to the power of minus 1. And if you want, this is rule, what rule is this? Rule 4. The rule which says that you can move, this is the same as 3 to the power of 1 on the bottom. The rule that says that you can move exponents up and down fractions. but you have to change the sign of the power. So you move the 3 to the 1 to the top, and it becomes 3 to the power of minus 1. Okay, so you use rule 4. So now, towards isolating the x, let's try to make this minus 2/3 into a 1. Let's try to make this minus 2/3 into 1, and we use the same trick as in the previous example. So what times minus 2/3 is 1? What times minus 2/3 is 1? Minus 3 over 2, right? So then you take both sides to minus 3 over 2. Okay, basically, it's the same trick as in the previous example. You take both sides to the power of minus 3 over 2. And that's because minus 2/3 times minus 3 over 2 is 1. Okay, so it's the same trick as in the previous example. Take both sides to the power of minus 3 over 2. Okay, so you take the left-hand side to the power of minus 3 over 2. You have to take the right-hand side to the power of minus 3 over 2. And as I said, this is the same trick as in the previous example. Same trick as previous example. And what I'm using is the fact that, just looking at the trick from the previous example, you're using the fact that minus 2/3. The reason why I chose minus 3 over 2 is because minus 2/3 times minus 3 over 2 is 1. Okay, so that it's that trick from the previous example. Is this clear? Okay, it looks like it's clear. Okay, so using the same trick as in the previous example. So I took it both sides to the power of minus 3 over 2 because minus 2/3 times minus 3 over 2 is 1. Okay, and it's using that trick from the previous example. Okay. Okay, so now what do we have? We have repeated exponentiation, right? We're taking this expression inside parentheses, x minus 1 divided by 2, and we're exponentiating by taking to the power of minus 2/3, and we're exponentiating again by taking to the power of minus 3 over 2. So we have repeated exponentiation, and remember the rule which says that repeated exponentiation is the same as multiplying the powers together. But we chose minus 3 over 2 in such a way that minus 2/3 times minus 3 over 2 is 1. So then, if we multiply these two powers together, we get 1. So we just get x minus 1 divided by 2, right? Because anything to the power of 1 is itself. And the same thing, over here, we have a repeated exponentiation. And by the rule, repeated exponentiation is the same as multiplying the powers together. Minus 1 times minus 3 over 2 is just 3 over 2. So it's just 3 to the power of 3 over 2. So we're using the rule 2. Which says that repeated exponentiation is the same as multiplying the powers together. And then now it's not so hard to isolate the x. First, remove this 2 by multiplying both sides by 2. So x minus 1 is 2 times 3 to the power of 3 seconds, 3 halves. And then you bring the minus 1 to the right. X equals to 2 times 3 to the power of 3 over 2 plus 1. Okay. So I'm finished for today. Okay, so see you again later.